Okay, so hello everyone. We are going to start a new topic today, which is multi-threading, right? So till now we have discussed about processes in detail. So we have understood what a process is, how processes are scheduled and so on. In this lecture, we will start discussing something else called a thread, and we will understand the difference between thread and process. So let us start with first discussing what is a thread. So we have already understood that a process is a program in execution. But what we have understood is that a process is a program in execution with a single thread of control. That means you have uh, you have the set of instructions, and we understand that what control is. So control is maybe control starts from within the main function in a C program. So it starts with the first line of main, and then it proceeds according to the rules of the C language. So if there is a for loop, then it behaves accordingly and so on. So this is the thread of control. Now, all modern operating systems allow a process to have multiple threads of control. Right? So multiple threads of control going on concurrently. So for example, let us take the example of a word processor, like MS Word or something. So there are different tasks that are possibly going on at a certain point of time inside that same program, inside that same word processor. Say it's updating the display based on what keystrokes are being given. Also, there may be some other keystrokes which do not result in update of display, but it results in something else, maybe saving something or whatever. Then it may do a spell checking. Now, so it's quite possible that at a certain point of time, these three activities are going on together. So if you have a single thread of control, then it would be difficult to do all these three together. So the operating systems allow a task or allow a process to have multiple threads of control. Say for example that you have given, so you are running a program, some kind of process, an application, and you have asked it to download a large file. And simultaneously you want to go on typing in that same processor. Remember, I am not talking about two different applications, right? But it always happens, many times happens that like you are running this browser. On one side download is going on, but on another side you are filling up a form. Maybe you are logging into your mail account, etc. How is the browser doing both these things seemingly together? If it think about it, if it has just one thread of control, then that thread should be busy with the download because you have given it a large file to download. In that case, how is this process also allowing you to log into your mail? Such things happen because operating systems allow a process to have multiple threads of control. Right? So what is a thread? A thread can be considered a basic unit of CPU utilization. So a thread usually has a unique thread ID, its own program counter, register set and stack. If you observe carefully, these things, program counter, register set, stack, these we were discussing till now in the context of a process. That a process should have its own program counter value, registers, contents, stack, and we discussed that say when one process is being switched out of the processor, these things need to be saved so that it can be resumed from at a later point of time. So we have discussed these things, but in the context of a process. Now we are saying that the same process can have multiple threads of control, and each thread will have its own copy of program counter, register set, stack, and each thread will have its thread ID. However, the important thing to note is that this, all threads within the same process will share some information. For example, it will share the code section, the data section, other OS resources like open files and so on. Okay. So now the picture that we are getting is this. Okay. Yeah. So essentially all threads of the same process are sharing the same virtual memory address space. Essentially the picture we are getting is this. Till now we were talking about this model which is being shown now. So you have this process which has the code segment, data segment, some open files. It has its register values, the stack, and there is a single thread of control. This is what we have discussed till now. At present, we are discussing this model, which is shown on the right. Now, this process is allowed to have several threads of control. Each thread has its own registers, stack, etc. Because remember that, this thread may be executing a particular function in the code, and this thread may be executing some other function in the code. As I said in the example, maybe you are running a browser, one thread is downloading a file which you have asked it to download. Maybe that will take 5 minutes to download. Meanwhile, you would also like to log into your mail, etc. So another thread is helping you to log into your mail. It is accepting your keystrokes, it is communicating with the mail server and so on. Now each thread has its own registers, stack, etc. However, all these threads inside the same process also share some information, like the code segment, the data segment, the open files. These things are shared by all threads. Okay. So we will definitely discuss more about threads. So for example, our next question is, why do you need threads? Let's understand that, then I can take your questions. So why should we suddenly go from one thread of control to multiple threads of control? Why do you think we need threads? Maybe some guesses. Why do we need threads? Why should we at all want to have multiple threads of control in the same process? If you have any answers, please write here. Okay, I've got two good answers. Any more? Okay. Good. We have got some good answers. Okay, I think someone is unmuted. Please mute yourself, everyone. I'm getting some noise. So please, everyone, keep yourself muted. If you have any questions, etc., please write here. Okay, first of all, let me go ahead with why do you need threads? Then I can answer a question by Rashil. Okay, so first of all, why do we need threads? Some good answers have come. One thing is definitely speed up, like the example I was giving. So in this browser example, one option can be that make the user wait until the download is complete. Okay, so if the download takes 5 minutes, let the user wait for 5 minutes. But that is not, a good design. What would be better is the download happens in the background and you do your work. So that means this browser, we want it to do two things concurrently. So that is definitely one reason for using threads. The other reason which some of you have interestingly identified is something about efficiency. So like Shubham said, processes are heavier to use. Srihash said that sharing data between threads is easier than processes. Why? Why do you think, Srihash or Shubham? Maybe you can unmute yourself also. Why do you think this is the case? Or what do you even mean? Processes are heavier to use means what? Or maybe Srihash, what do you mean by sharing data between threads is easier?
Sir, according to how we did inter-process communication earlier, we would need to create a pipe or something like that in order to share data between two processes. If we use threads, we can just use the shared data segment to have common variables for two different threads.
Very good answer. So let me go back to the picture once. See, we have discussed processes and we have discussed that processes can talk to each other. And we have discussed mechanisms like inter-process communication mechanisms. We discussed pipes, messages, etc. But then we need kernel support, right? So if you want to write to a pipe, there will be a context switching overhead. The pipe will have to be maintained by the kernel and so on. But here, see this picture, the data segment is shared by all the threads in this process. So now between two threads of the same process, they do not need to depend upon kernel structures like IPC to talk to each other. They can simply use the data segment because it is shared between all the threads. So that makes communication between threads much faster. Right. Similarly, okay, there is so you understand that threads have these advantages. I mean, the two threads within the same process, they can communicate much more easily. Also, another thing to note here, I just want to show this picture and tell this. And next, what I'm going to say is kind of related to what Rashil asked. So the question Rashil asked is, can multiple threads started by the same process run simultaneously? Okay, let me ask you, some of you, what do you think is the answer? Can multiple threads started by the same process run simultaneously? Exactly what Shrihas said. The answer is no, because again, we still have only one processor. Okay, we still have only one processor. So just like two processors could not run simultaneously, two threads also cannot run simultaneously. They'll have to be scheduled. That's why I am not using the term simultaneously. I am using the term concurrently. Right? So the processing model has not changed. We still have one processor. And some thread has to be scheduled to run on the processor. Okay. So now you understand. So I hope that Rashil's question is answered, that threads don't run simultaneously. Just like processes, threads also run concurrently. And therefore there is a need for context switching, etc. even among threads. But herein comes the second big advantage of threads, something which Shubham or Mukul pointed out. If you want to context switch one process and bring in another process, there is a big overhead. We have discussed this, like all the core segment, data segment, etc. All the registers, stack, etc. they need to be stored. And then the next process needs to be loaded and so on. So there is a big context switch overhead. But if you are switching from one thread of the same process to another thread of the same process, the context switch time is very small. Because again, you don't have to bring back in the code, data, open files, etc. Only maybe the registers and the stack. This needs to be saved and then brought back in. Right, so this is another big advantage of threads. Like context switch between threads is much faster than context switch between processes. Okay. So basically threads have these, I mean, this we'll see, but just to summarize, threads have these advantages. First of all, it allows a process or a program to do multiple things together. Again, together does not mean simultaneously. It still means concurrently, but then it allows the program to do several things together. Like that example, again, I keep going back to it. Suppose your browser, you are using it to download something, download a large file, as well as you are checking mail. So the same program is allowing you to do two things, again, not simultaneously, but concurrently. But of course, to a human being, it will appear simultaneous because we have discussed that the CPU is switching between processes or switching between threads very fast. Okay. That's one advantage, the usable advantage of threads, and the efficiency related advantages are these two, that threads are much lightweight. Threads are much lightweight. So context switching between threads, etc., that is much faster. And also threads can communicate among each other much quicker or much efficiently because they don't need to depend on the kernel. So every time a process writes to a pipe, etc., there is a system call, right? So a context switch has to happen. Those things don't need to happen with threads because threads have this data segment common. They can simply talk to each other at the user level or at the process level. They don't need kernel support to talk to each other. Okay, I see the question by Pankaj, but I'll answer that a bit later. I mean, the answer is included in the slides. It will come a bit later. Okay, let's proceed. I mean, we have kind of understood the motivation. Still, let us discuss once. Why do you need threads? Just as we discussed, context switching among threads of the same process is much faster. So the OS needs to reset or store much less memory locations registers. Next, responsiveness is better. This is the usability part that I was telling. And it is important for interactive applications. So just as I was saying, maybe a large file is being downloaded by your browser. So a part of the process is busy. Even then the interface works. It still allows you to browse other pages or check your mail, etc. So for interactive systems, having multiple threads is kind of a necessity nowadays. Otherwise, we will not like to use that kind of a application which has only one thread of action. Next, this is also what we have discussed. Resource sharing is better for peer threads. When we use the term peer threads, we usually mean threads within the same process. So the main advantage is that the data segment is common among all the peer threads. Therefore, you can simply share variables, etc. You do not need to use system calls to do IPC. Like pipes, shared memories, etc. you do not need to use anymore. Two threads can simply utilize the shared data segment and communicate. So shared data segment is shared, open files are shared. So it's much simpler to communicate using these, or much more efficient to communicate using these rather than say pipe, shared memory, etc. Also, thread creation is much easier or much more efficient. So process creation is heavyweight while thread creation is lightweight. Again, why? Because not all, for creating a whole process like using fork, the whole address space has to be copied. But here, if you are creating a new thread within your process, then the code segment, data segment, etc., those large segments do not need to be copied. You simply have to copy a smaller amount of information like the stack, the registers. Right, so process creation is heavyweight and while thread creation is lightweight. In fact, there have been some statistical studies done, and it was reported that depending on the operating system, thread creation can be 10 to 30 times faster than process creation. And finally, threads offer better scalability for multiprocessor or multi-core architectures. Now, as I have told you, in this basic level course, in this basic level operating system course, we are not considering multiprocessor or multi-core architectures. Right, but this is just to tell you that why have threads become so popular, is that nowadays most processors are multiprocessor or multi-core. So if you go to the market today and buy an Intel processor or something like that, you will most possibly get a processor which will have at least 4 cores, etc. Right. So nowadays that is the trend, because we want more and more parallelism. So if you have more threads, then that will help you in assigning them to multiple cores and so on. Yeah, so this point we are not going to discuss in this course. As I said, this course will only consider uniprocessor systems. But maybe some of you know our department offers an advanced operating system course also. So if you are really interested to know about multiprocessor or multi-core architectures, I would suggest you to take that course in a subsequent semester, the advanced operating system course. Okay, so yeah, just some more motivation of how are threads used in the real world. In fact, many of the programs or applications that we use in real world are multi-threaded. Let's just briefly discuss 3 examples: a web browser, a web server, and an OS. So a web browser, I have already discussed that you might be using your browser to download some data, to display a complicated web page, a big web page. Additionally, you are also checking your mail, and your browser is waiting for your password input. So all these things can be handled by different threads. In fact, you might be surprised to know that sometimes, suppose you have asked the browser to suppose you have asked your browser to show you a very big web page having many images, etc. To speed up such things, often multiple threads are used to download parts of the same web page. Typically, one design is that every image will be downloaded by a different thread, because an image does not have to be only downloaded, it has to be rendered. So rendering is an operation. Feel free to look this up. But basically, every image, it's a design that every image is rendered by a different thread, so that the whole web page can, come up quickly. So if it is a very big web page having maybe 15-20 images, then it is quite possible to utilize multiple threads to even show you that one web page. Okay. So this is about a web browser. Next is a web server. So let me ask you here, in your networks course, have you designed a web server by now? Some kind of server, like server client setup. Have you designed a server by till now? Okay, so maybe you have designed a UDP server. Threading was not needed, fine. But I'm sure that as you go ahead in that course, maybe some subsequent assignment, we'll ask you to design a server which will use threads. The reason is this. So again, I hope that you will get some idea of what I'm saying from your networks course knowledge, that a server usually listens at a socket or something. Okay, So it is listening for new connections, new connection requests. So suppose a connection request comes. Now if the server, so suppose you have a function which handles or answers a client request. So the client is connected to the server. Now the server needs to do something to address that client. So think about it. Suppose the server is running, it is listening at a socket on a port. A connection request comes. The server goes into that function, which a control goes into that function which will address this request. But then there is a problem. No one else will be able to connect because the server is in that function where, the job is now to handle that connection which earlier came. So no future connection can come. So usually that is not how servers work. When a new service comes, when a new client request comes, usually a new thread is created. And that new thread services that request or talks to that client. Whereas the main server process, that goes on still listening at that socket for new connections. So every time a new connection request comes, a new thread is created. And that thread handles that request. Meanwhile, the server, the main process, the main thread you might say, that is going on listening for new requests and so on. Okay. So I'm sure you will design such multi-threaded servers soon in your network lab course. Or maybe, maybe processors can be used, but I guess, I'm not sure, but maybe you will be asked to write a multi-threaded server also. But I hope you understand the picture that many people need to be served by this server. And so there will be a thread allocated to address every client request, while the main thread goes on listening for new requests. The third example is, of course, what we are discussing, operating system. So actually several threads operate in a kernel. So some thread may be managing the memory, some thread may be managing the device, some thread is handling interrupts and so on. So usually modern kernels are multi-threaded. Okay, so this was just a brief description of several systems which maybe we are not conscious, but we are using many systems or many programs which are based on a multi-threaded design. Okay, now I will discuss about multi-threading models. Before that, any questions? There is one question which I have not answered, that will come. The question by Pankaj. Do different threads of a process get its own CPU time, or do they share a common process time quantum? So multiple answers are possible, but we will come across them. Any other question? Okay, if not, let me proceed. Okay, there is a question. How can threads share the same address space but have separate stacks? Would it not be possible for one thread to access another thread's stack? Okay, I'm not fully sure of the question. So see, the support for threads must be provided by some library, etc. So, okay. My basic answer is, okay. So Srihash, maybe unmute yourself. I did not quite understand the question. What do you mean as in? Let me say this and then I can hear your side, that threads need to be supported by some library, right? And we will discuss one such library. So basically, how will you create a thread? Possibly by using some system call kind of thing or some library at least. So the different stacks, etc. will be maintained by that library. So when you get a thread, Okay, maybe this question could be answered a bit later, but anyway. So when you create a thread, that comes with its stack, or that comes with its attributes, which we will see. And like that library possibly will not give any way of one thread accessing the thread of another library. So I would say, okay, a standard library, which one of which we will discuss, will not allow this. However, if you ask that can this be done, then that's an interesting question. Suppose you are designing your own thread library. Then whether this can be done or not, that I am not sure. But Srihash, I mean, if this does not answer your question, then please unmute yourself and tell me what you meant.
Yes, sir. Basically, I was asking, for example, we have the shared data segment. So suppose I declare a global variable which has a pointer. I use one thread and I pass the address of its stack to another thread. So can that other thread use the global variable to access this stack, for example?
Okay, we will soon see that the thread library that we will discuss, actually, according to that library, any global variable is shared between threads. Okay.
Right. So the pointer would be shared, but would the stack be accessible also with which is the location of the address?
Okay. Yeah. This is what I also understood your question to be. My answer is that if you use a standard thread library, then it should not be allowed. The thread library will, constrain you to use your own stack, or constrain the one thread to use its own stack. However, whether it can be done is a different question. Suppose you design your own thread library without relying on any standard thread library, you design your own thread library, then whether this can be done, this I am not sure. Theoretically, it may be, because after all, they are all part of the same address space. But then you possibly have to design your own thread library for doing this.
Right, sir. So there's definitely no issue of one stack like clashing with another one, right? That's like probably guaranteed.
Yeah, that is handled by the thread library.
Oh, understood.
But if you ask a theoretical question, like both are within the same address space, then theoretically one should be able to access the another. Yes,
Right.
that part I'm not sure, but I think that if you design a thread library, like if you are working on threads without using a standard library, which of course will require much more advanced programming, then it might be possible. This I am not sure.
Right, sir. Okay.
But a standard library will prevent these things from happening. Okay, any other question? Okay, so let's now proceed towards studying in a bit more detail how threads work. So basically there are two types of threads, user threads and kernel threads, sometimes also called user level threads and kernel level threads. So the user threads or user level threads are managed by some thread library, which works at the user level usually. So there are a few well-established primary thread libraries like POSIX pthreads, Windows threads, Java threads, and so on. We will discuss about pthreads in some detail. So these libraries, that's exactly what I was telling Srihash, these libraries will make it easier for us to use threads. Right? But these will run at the user level itself. It's just like a C library. This is a threads library. The other kind of thread is kernel threads, which are supported and managed by the kernel itself. And nowadays, all general purpose OS like Windows, Linux, Mac, all kind of support kernel threads. Now, as you might have guessed, user threads will ultimately need kernel thread support to run. Right. So after all, user threads will also have to be assigned to the processor. And so possibly, okay, coming to it, what the kernel will schedule is the kernel threads. But the user threads will be mapped to the kernel threads somehow. Okay. So possibly the kernel will schedule the kernel threads. but in some way the user level threads will be mapped to the kernel threads. And how is that mapping going to work? There are many choices. Many to one, one to one, many to many. So we are discussing how to map user threads to kernel threads. So in the many to one architecture, many user level threads are mapped to the single kernel thread. Okay. So the user threads are managed by the thread library in the user space, and the kernel thread is managed by the kernel. So the mapping is many to one. Now there is a problem with this many to one mapping, which is this, that a blocking call by one thread causes all threads in the process to block. Okay, first of all, what is a blocking call? What do you mean by a blocking call? Or can you give some examples of blocking calls? Yes, IO. Any other answer? Something we have discussed? Okay, sleep. Yes, exactly. Wait. So basically, a blocking call is a system call which will not allow the process to proceed unless that call is handled. Okay. Okay. Interrupt is not a blocking call. So interrupts usually do not. So interrupts are not generated by this process itself. Interrupts usually come due to external events. Maybe a timer interrupts or some IO device interrupts. So interrupt is not an example of a blocking call. When we say a blocking call, we usually mean some system call or some function call which this process has made. But such a call such that the process won't proceed until this call returns. Typical examples is scanf. So after all, in the C program we write scanf, and that gets translated to read at some lower level, maybe the C library or something like that. But ultimately it's a blocking call. Unless that data has been read, it won't proceed. Similarly, wait. If a parent decides to wait for a child to terminate, then it's a blocking call, right? So by the way, so again, just to drive home this point, what can a blocking call immediately return, or does it have to block for some time? So can a blocking call immediately return, or does it have to wait for some time? Or does it have to block for some time? Yes, a blocking call need not always block, right? So for example, yeah, so suppose you have issued a scanf statement. We discussed this point that there is actually an input buffer associated with every C program. So if some data is already available in that input buffer, your scanf may not block. There is already data buffer, input data buffer. Similarly, suppose a process calls wait, but the child has already terminated. It can happen, right? So suppose the parent created the child, the scheduler scheduled the child first. It was a very quick process, it completed very quickly. Later the parent was scheduled, the parent then called wait, but by now the child has already terminated. So the wait will not block anymore. Okay. So don't be under the assumption that a blocking call always has to block. But yes, there is this possibility that a blocking call will block. As in, a blocking call will not allow the execution to continue until it has been addressed or until the call returns. Okay, so the problem with many-to-one mapping is that a blocking call by one thread will cause all the threads in this process to block. Okay, and that is why nowadays this model is not very popular. Many to one is not very popular. Another reason, of course, is this, that multiple threads may not run in parallel or multi-core systems because only one can access kernel at a time. Because only one kernel thread has been assigned to all of these, right? So for all these reasons, this model is not very popular nowadays because nowadays people are going for multi-core systems, etc., etc. So many to one is not much popular nowadays. So let's see the others. One to one. Okay. Here every user level thread is mapped to a individual kernel level thread. So that means that every time a user thread is created, the kernel will also have to create a new kernel thread. Right? So of course this has some advantages and disadvantages. Advantage of course is much more concurrency than many to one. Right? So even if say one thread makes a blocking system call, the others can run because more kernel threads are available to support them. However, the problem is that the more user level threads are created, the kernel will also have to create that many threads, and that's an overhead on the kernel. So therefore, the number of threads that a process can create, the number of user level threads that a process can create is sometimes restricted. I mean, if everyone starts to write a program which creates 1,000 threads, then the kernel will simply be caught up in creating too many kernel threads. And remember, kernel threads will have to be scheduled, etc. Therefore, a lot of overhead will increase. Therefore, threads per process, like the maximum number of threads that a process can create, is usually restricted. So this idea is used in Windows, Linux, etc. So as you understand, there are these trade-offs. In many to one, the kernel overhead was very low, but then concurrency was happily suffering. In one to one, there is much more concurrency. Every user thread can proceed independently, but there is a lot of overhead for the kernel. So whenever there is this trade-off, system designers try to go for a intermediary approach, like best of both worlds kind of thing. And therefore, this has come many to many model. So here, many user level threads are mapped to many kernel level threads. But of course, the number of kernel level threads is usually much smaller than user threads. So maybe I'm just giving some numbers from my imagination. Maybe 100 user threads are mapped to 8 kernel threads. Maybe. I mean, don't take these numbers very sacrosanctly. These are just imagining. So basically, here the kernel will create a sufficient number of kernel threads, and that will be it. Like it won't go on increasing kernel threads as and when more user threads come. Sure, it can. Maybe it can say that, okay, after every 20 user threads are created, a new kernel thread will be created. That is possible, but it is definitely not going to create a kernel thread for every new user thread. That won't happen. Right. So many user threads will be mapped to several kernel threads, but of course the number of kernel threads would be lower than the user threads. So as you understand, this is a kind of mix of both worlds. So some concurrency is there because say one user thread which was mapped to this kernel thread makes a blocking system call, then okay, this kernel thread blocks, but then the other kernel threads can still be scheduled. At the same time, the overhead on the kernel is not as much as say one to one because a limited number of kernel threads are being created. Okay, so this was a kind of a high-level discussion that how can the kernel assign user threads to kernel threads. But the main takeaway is that there are these two levels of threads, user level threads and kernel level threads. So kernel level threads would be the ones that would be scheduled, and there would be some mapping between user level threads and kernel level threads. How to do the mapping? There are these different approaches. Okay, so till now the discussion has been a bit abstract and high level, but now let us actually go into the detail and see how threads work. And for that we will discuss a particular thread library which is quite popular, and it's called the POSIX thread library. So first of all, what is a thread library? Okay, Akshat has a question. Is the Python interpreter lock somehow related to many-to-one threads? Okay, sorry Akshat, I am not aware of Python interpreter locks. Okay, so yeah, sorry, I cannot answer this question. Okay. Any other questions? But it can also lead to inefficient use of threads. For example, if you have 4 user threads, but kernel only use 3 kernel threads. Yeah, sure. So Pankaj, of course, and that is why I said, I mean, probably the system, probably the mechanism will be such that as more and more user level threads are created, the kernel will create some more threads. Like, of course, if you have 4 user threads, the kernel will not create 3 kernel threads. Right. So the set of kernel threads may not be, or the number of kernel threads may not be completely fixed. So it might be the mechanism that for every 10 user threads created, the kernel will create a new kernel thread. Okay. But the idea is that the mapping is many to many. Okay. Okay, let us give the basics of the thread library, then the actual programming possibly we will discuss tomorrow. So first of all, what is a thread library? Just like a C library or something like that, it provides the programmer with an API for creating and managing threads. Now, there are 2 types of implementing a thread library. One is to put the library in the user space. That is, all code and data structures of the library itself exist in the user space. The other option is to provide a kernel level library. That means the code and data structures of the library exist in kernel space. That means invoking a library function results in a system call. So in this particular scenario, when the library itself is in the user space, then calling a library function will not result in a system call. It will just be a function call from like a function call in the user space itself, right? However, in this second option, that if you design a kernel level library, then invoking any library function will mean that the control has to go to the kernel, which will happen through a system call. Okay. Okay, so what we are going to discuss is pthreads. So there are several popular thread libraries. Actually, the textbook, the Galvin, actually has some discussion on all of these. But in the class, we will only focus on POSIX pthreads. Also, before going actually into the thread library, it's something has to be, one thing to discuss. So there are usually 2 strategies for using threads. This, of course, is depending on how you write your code. Let's understand the strategies. One is asynchronous threading. And of course, the other would be synchronous threading. But let's understand the difference. So in asynchronous threading, the parent thread creates 1 or more child threads and then resumes execution immediately. That means the parent and the child are executing concurrently, and parent is not waiting for the child to terminate. So the parent creates several childs and they execute concurrently. Each thread runs independent of others, and parent need not know when the child threads terminate. So the parent is not waiting for any child to terminate. Typically, this asynchronous strategy is used when there is very little data sharing between threads. In contrast, there is this strategy of synchronous threading. Here, the parent creates 1 or more child threads and then waits for all the child threads to terminate before it resumes. So this is the important thing. In the synchronous threading, the parent is waiting for all child threads to terminate before it resumes. But in the asynchronous threading, parent and child are proceeding concurrently. Parent is not waiting for the child to terminate. So this synchronous threading is also called the fork join strategy. Which one to use? It typically depends upon your application. If you have an application where data sharing between threads is not much needed, then you can go for asynchronous. For example, like in the server example, web server example, maybe the server is creating one thread to handle every client request, and there is no feasible reason for one thread talking with another thread, because they are handling completely different or unrelated client requests. Then maybe the asynchronous threading can be used. But think of another application where maybe there is a big data structure, a big array or a big database, and some search needs to be done on that big database or array. If you use one thread to search through the whole array or database, it will take a lot of time. Therefore, your process has created 5 different threads, and that 5 different threads will do the operation on 5 different parts of the array. In such cases, there is a big need for data sharing among threads. And also there is a need that after every thread terminates or after every thread does its job, the parent will have to take the answers given by all the 5 threads and then do some computation maybe. Right? So maybe it's a simple like summing of a big array. So you divide the array into 5 parts and allocate 5 different threads to sum up the 5 parts. And finally the process will add up all the answers given by the 5 threads. In such cases, the parent should wait for all threads to terminate and then should do something with the answers given by every thread. So in such cases, synchronous threading is used. Okay, so this was just to understand how different threads are used. So our next topic will actually go into the POSIX threads. But since it's already time, I think it would be better to start this tomorrow. So if you have any questions, you can ask. Otherwise, we can end this class. Fine, let us, okay. There is a question, what advantage do we have in using multiple threads in terms of throughput, considering only one processor? Again, I'm not sure of the question. So, Rutav, can you maybe unmute yourself and say?
So, if all these threads run under single process, right? So, the scheduler will schedule the process. And if there is only one process, one of the thread is executing at a time. So, in terms of throughput, is there really an advantage when we consider only a single processor?
You are right. So, if you consider throughput, then and if you have a single processor, then there might not be much of an advantage. The threads have become mainly popular because nowadays multi-processors or multi-cores are being used. Like even a normal PC nowadays has a multi-core processor having say 2 cores or something, or often 4 cores. So for a single processor it might not give much advantage for throughput, but then the whole concept has come because of, the whole concept has been popularized because of multi-core or multi-processor architectures. Okay, and Ramnivash has a question. Could you give some example where asynchronous or synchronous threading is used? I gave the example, right? So just again, these examples are coming from my imagination. Therefore, so suppose you have an application where different clients are connecting to a server, and there is no point of having communication between one client and another. Just an email server, like say you will log into your email, someone else will log into their email, etc., etc. So there is no concept of one thread having to communicate something with another thread, or one thread having to share data with another thread. So in such cases, asynchronous threading can be used. The principal process, the parent process, will say create a thread for every new connection request, and that thread will handle that connection, that request. I mean, there is no data sharing, or the parent does not even wait for child to terminate, because who knows how long you will check your mail. Right? So as long you will check your mail, that thread will work. After that, it will terminate. So the principal process, the parent process, does not need to know when that thread will terminate. But on the other hand, think of an application where you are maybe summing the elements of a large array, a huge array. And if you sum like from 1 to n just sequentially, it will take a lot of time. So you divide the array into 5 parts and you create 5 threads. So your parent process creates 5 threads, each one of which will sum up the elements in 1/5 of the array. In such cases, first of all, there should be some data sharing among the threads, because every thread will have to know what are its limits. Right? So maybe every thread will know that what are the bounds, array bounds, inside which it should work. And also, more importantly, the parent process will have to take the sums computed by these 5 threads and then give the total sum. So this is a synchronous threading example where the parent will have to wait for all children to terminate, and then it should possibly do something with the results returned by the 5 different child threads. Okay, so depending on the application, you choose asynchronous or synchronous threading. Okay. Fine, then let's end this class. We'll continue tomorrow with the PostX pthreads library. Okay, Shubham is asking, it's off topic, but can you tell us what tests we need to perform in lab? The make check. Okay, in that case, I would suggest you inform of this problem in that Teams window. I mean, in Teams, in the lab channel, inform of this topic, inform of this problem. So make check command is not working for many of us. Okay, but you inform about this. Right. I mean, ideally, this problem should have come up a few days earlier. But then, well, I mean, tomorrow being the deadline, I would have expected, or it would have been better if this problem would have been reported a bit earlier. But anyway, report it in the lab channel. I'll discuss with Professor Mondal and get back. Okay, so one of us will get back. Fine then, let's end this class. We'll continue tomorrow.